Complex systems, they have this way of creating an illusion of stability. They just seem to work, day in and day out, operating reliably in the background. And then, all of a sudden, they just don't. The real puzzle isn't really that they fail, but how one single, seemingly tiny crack can bring the entire structure tumbling down.
So, to really get a handle on this phenomenon, we first need to dismantle a pretty common illusion about why big things break.
Our intuition, it tells us that a massive failure must have a massive cause, right? Some single catastrophic error. But in the real world, large-scale collapse, it rarely works that way. It's not about the size of the initial shock. It's really about a small trigger hitting a system that was already quietly vulnerable, a system that was basically ready to unravel.
To see how this actually happens, we need to look past the specifics of any one system, whether it's a power grid or a financial market or a supply chain, and instead, we need to examine the underlying blueprint of the system itself.
At its most basic level, a system is really just a set of interconnected parts, and that critical feature is the interconnection. It's what allows the whole thing to work. But as we're about to see, it's also the source of its fragility.
The dynamics of pretty much any system like this can be understood by breaking it down into 4 fundamental elements.
So first, you've got the components themselves, the individual parts or nodes. Second are the connections, the links between them. Third is the stress, or the load, that's placed on each of those components. And finally, there's tolerance. That's the maximum stress each part can handle before it just breaks.
Okay, so when you put these 4 elements together, they create the perfect conditions for a very specific type of failure mechanism, one that lets a small problem grow exponentially. Let's start with a system that's in a stable state. The load is distributed evenly across all the components, and every part is operating well within its capacity. The connections are what let the system work together as a whole.
Now, let's say a single component fails. This could be for any reason, a random event, some external shock, or just simple wear and tear. On its own, the loss of one little component, well, it seems pretty insignificant.
But here's the thing. The work that component was doing doesn't just disappear. The system's connections, they immediately reroute that load onto its direct neighbors.
This sudden spike in stress pushes those neighboring components way beyond their tolerance level. Their load now exceeds their capacity, and that causes them to fail too.
And now the failure of these parts redistributes their load plus the extra load they just inherited. And this is where you get a positive feedback loop. Each failure triggers more failures, and the damage starts to cascade right through the network.
This is what we call a cascading failure. It's more than just a simple chain reaction. It's a process where one small local event can progressively trigger the collapse of a huge portion of the entire system.
So this cascade dynamic, it leads to some really counterintuitive results. It shows us that in these complex systems, our normal, everyday assumptions about cause and effect often just break down.
For example, it seems perfectly logical that if you increase the tolerance of every component, you should make the whole system more robust. But it turns out that's not always the case. Studies actually show this relationship can be, well, it's not a straight line. A system with low tolerance might have frequent but small failures. A system with very high tolerance, on the other hand, might survive most disruptions without a scratch. But it's that system in the middle, with medium tolerance, that can sometimes suffer the worst damage. Why? Because it's just strong enough to prevent all the small failures, which allows stress to build up to really critical levels before the whole thing collapses catastrophically.
What's more, the outcome of any disruption is often bimodal. Now, what that means is the system tends to have only 2 main responses to a shock. Either nothing serious happens at all, or everything collapses. There is very rarely a middle ground.
And the final outcome is incredibly sensitive to that initial trigger. The failure of one component might just cause a minor flicker, but the failure of its identical neighbor, right next to it, could ignite a system-wide collapse. This makes trying to predict the consequence of any single failure nearly impossible.
So when we put all these pieces together, a completely new picture of system collapse starts to emerge.
System-wide collapse is not the fault of one broken part. It is an emergent property of the entire system. You could say the failure isn't in the system, it is the system, behaving exactly as it was designed to under stress.
Think about it. The very connections that allow a system to work so efficiently are also the exact pathways that transmit failure. Interdependence is a real double-edged sword.
It enables the collective function, but it also creates the potential for these devastating cascades.
And this means that the final size of a disaster isn't determined by the initial spark. It's determined by the architecture of the system itself, its web of connections, its loads, its tolerances. The outcome was basically written into the blueprint long before the failure ever began.
So, what does all of this reveal? Well, it shows us a fundamental paradox that lies at the heart of every single complex system. The very design that creates efficiency and strength is the same design that creates the pathway for total collapse. Failure, then, isn't some kind of outside threat, it's a possibility that's woven right into the fabric of the system itself.